Hello, welcome to today's seminar. Our speaker today is Borut Lujar from Slovenia, and he will be speaking about strong edge colorings of maybe cubic graphs. Right, welcome to the seminar.
Thank you. So it will not be just about strong edge colorings, but about a whole class which covers both proper edge colorings and strong edge colorings, in fact. This was a topic that we started to explore with Hervé Ocar and Dimitri Lejoux from Bordeaux in France. And I come from Slovenia, as Bernard mentioned. I was thinking if I should introduce a little bit Slovenia since I am from another continent, but probably you all know by now from the last 4 years the country. Maybe it's not clear to me whether it's more famous in USA by Melania or by Luka Doncic. Hopefully, at least by one of them. And let's start. So, whoa. I would like to start with some definitions, just that we are all clear what I'm talking about during my presentation. So for me, subcubic graphs are graphs with maximum degree 3. Usually in this class of subcubic graphs, also the graphs with maximum degree 2 and 1 are counted, but just for simplicity of presenting the results, I will stick with maximum degree 3 graphs. Whenever I talk about graphs, I mean simple graphs, because with multi-edges, then you have to be a little bit more careful when talking about the special examples achieving some tight bounds. So let me just limit myself to simple graphs. And another notion which might cause some confusion is the distance between the edges. By the distance, I mean the distance between the two edges, between the vertices in the line graph, between the corresponding vertices in the line graph. So if we have in our graph two edges which share an end vertex, then I say that they are distance 1, like these two, A and B. And if the two edges are just connected by another edge in a graph, then they are at the distance 2, like the edges A and C. And also, for some results, I just adjusted the formulation to fit in my notation during this talk. If we repeat a little bit what a proper edge coloring is, in a proper edge coloring, we are coloring the edges in such a way that they receive distinct colors as soon as they are adjacent. So around every vertex, you need to have every edge colored differently. And by this, we get the lower bound for the smallest number of colors needed. The lower bound is just the maximum degree of the graph. By the definition, edges of the same color in a graph form a matching. And yeah, this notion, chromatic index, you probably all know. It's the smallest k for which we can color the edges of a graph properly. So I was not mentioning in the beginning, but Bernard was. We will limit ourselves to coloring of subcubic graphs only. This is because this class of colorings, which I will be introducing today, can be somehow motivated or put in a context more nicely if you have this maximum degree 3 behind. Of course, you can extend all of them to arbitrary graphs, but with subcubic graphs, the story goes more fluidly, more smoothly. And for proper edge coloring of subcubic graphs, we know by Wissing's theorem that 3 colors are always needed, and at most 4 colors are always sufficient to color a graph. Below here you have 2 examples. The left one is K4 with 1 edge subdivided, and this graph is the smallest subcubic graph which needs 4 colors to be colored. The right one is Peterson's graph, and it's the smallest bridgeless cubic graph. So it's a regular, cubic graphs are regular graphs with degree 3. And as you all know, this is the smallest known snark. It's the smallest known and the smallest de facto snark. So chromatic index of it is 4. The second notion, which is the second boundary of this talk, is the strong edge coloring. It's again a proper edge coloring, but we extend our requirement to the second neighborhood of the edge, of every edge. So if we have some edge colored with some color, then all the edges which are at a distance at most 2 from it need to get some different color from this edge's color. And again, by the definition, now we have induced matching when we are taking into account all the edges of the same color. Induced matching is a special kind of matching where all its representatives are at distance at least 3. Or with other words, the graph induced by the end vertices of the edges of this matching form a matching also. And the corresponding index will be called the strong chromatic index. The upper bound for strong edge coloring in subcubic graphs was proven by Andersen and independently by Horak, King, and Trotter. And it is 10 colors. Below you again have the subcubic graph which we can use to form other subcubic graphs or cubic graphs which need 10 colors. So that's a K33 with 1 edge subdivided. Every pair of edges in this graph is at distance at most 2, so we need to color every edge differently. And the right one, I was not aware of its name until I came to some seminar in Czech Republic in Pilsen. Do you know how this graph is called? Anybody? So I learned that if a graph is small enough and if it's regular, then it will have most likely a name. This one is Wagner's graph. Maybe it's not drawn in the usual way. Usually you have the cycle around and then all the edges are intersecting in the middle, in the center, but this is also one possible way to draw it. So Wagner graph. And as a remark here, it's class 1. It is 3 colorable with proper edge coloring, but it still needs 10 colors for strong edge colorings. For a strong edge coloring, which a little bit spoils my story here. You will see in the sequel why I am saying this. Anyway, so these are 2 boundary cases, a proper edge coloring and a strong edge coloring. And now I would like to put in the story some intermediate edge colorings, which will partially obey some restrictions. But before we go to that, I would like to introduce another notion, a notion of packings. Bernard is familiar with this notion? Maybe. So we say that a set of edges is a K-packing if in this set, every pair of edges is at distance at least K plus 1. So just an ordinary matching is a 1 packing because all the edges in it are distance 2 or more. and every induced matching is a 2 packing. And so on. Then in 2019, in a paper from 2019, Gastineau and Tony defined an S packing edge coloring, which is an edge coloring where for a given set S, not a set, sequence, sorry, non-decreasing sequence of integers, positive integers, we partition the set of edges of the graph into subsets x1 up to xl, such that each xi, each this subset, is an Si packing. So these integers just tell you in what kind of packing you would like to put some edges of a graph. So partitioning means that all these subsets are disjoint, right? And this S packing edge coloring just comes from the notion of packing colorings and S packing colorings, which was introduced before by Goddard. And so here are the references. I will publish these slides later on also on ResearchGate, so you can, if you're interested in this, just can check the references for that. I'm adding them in the slides also. Okay, let's take a look at an example. We have this Wagner's graph from the 2 slides ago. How can we color it? If we want to have this 1, 1, 2, 2 packing edge coloring, this is one possible way to color it. And there is not a lot of other possible non-isomorphic colorings of this guy in this setting. So 1, 1, 2, 2, what does it mean? We would like to have 2 1 packings, which means that we would like to have 2 matchings, 2 colors which form a matching, and 2 colors which form a 2 matching, 2 colors which form a 2 packing, so an induced matching. And we have them. These blue edges form a 2 packing because they are at distance 3 in this graph. So 1, 2, 3. The red edges are also a 2 packing. So the blue and the red guys are giving us these 2 sets for 2 packings. And then we have the orange and the turquoise colors, which are just a packing in this graph. So this graph has a 1, 1, 2, 2 packing edge coloring. And now if we expand our example a little bit, what is the smallest k so that we only have one color that is making a matching, that's a 1 packing, and all the other colors are forming 2 packings. How many 2 packings will we need in this graph?
This is the question?
Yes.
At least 3, K is at least 3.
At least 3, yeah. But this lower bound can be a little bit increased.
I can do 4. Maybe.
4 is not sufficient, right? You will need, so we already know that we need at least 2 colors for 2 packings, and we need to replace this 1 packing somehow. I mean, you will not be able to redistribute the colors in such a way that you will have just 1 color. You can have 1 color on 4 edges, but then you will need the other 12 edges to distribute into 2 packings. And since these blue and red edges are the only pairs of edges at distance 2 in this graph, all the other, at the distance 3, sorry, at distance 3 in this graph, you will need, if you want to replace, for instance, the orange color with 2 packings, you will need just to put on each orange edge another color. So altogether, you will need 6 colors.
If you do the opposite on the diagonally, they don't work.
Which one? For instance, this one and?
Oh,
This one.
The orange ones, I see. Like if you take the orange, yeah, yes.
They are at distance 2. You have here a connection, see?
Oh, I didn't see the cross edge. Yeah, good. Thank you.
It's too bright color, maybe.
No, I didn't realize. Good.
This is the specialty of the Wagner's graph, because that's also why it needs 10 colors for this strong edge coloring. So these blue and red edges are the only ones that are really far away. All the others are a little bit sneaky. So the answer here is 6. We need k equal to 6. Okay, and that's basically all the introduction I needed to have. Because I would like to consider the cases where I have in this set S of integers only 1s and 2s. So I can have only colors which form a matching, or only colors which form an induced matching. I'm not interested into colors which will require higher distance. So only 1s and 2s. Now, if we have in our set S only 1s, then we are in the proper edge coloring setting. We know that 4 1s will always be sufficient to color any subcubic graph. And this, I have such an abbreviation. I'm putting exponents for the numbers of 1s and 2s in my set, just to have it more, to have it written in a more compact form. So 1 to 4 packing edge coloring is possible for any subcubic graph. And if I'm only allowed to have 2s in my set S, if I only need colors which will be at distance at least 3, edges of the same color to be distance at least 3, then I will need to have at most 10 colors, and I will be happy because 10 colors are always enough for coloring a subcubic graph in a strong edge coloring setting. This is a strong edge coloring setting. So what we will be interested today is what is in between, if we have a little bit of 1s and a little bit of 2s. So let's start with replacing this last one with some number of 2s. This was investigated before this S packing edge coloring was defined. And it started with Albertson and Haas. So the color that appears the least number of times, usually in the literature it's called delta. It's not appearing that often. It's proven that it's more rare than the other colors. And Albertson and Haas proved that if G is cubic, then at most 2/15 edges are colored with delta. This 2/15, of course, comes from the example which you can all expect. It's the Petersen graph. In the Petersen graph, in the edge coloring of a Petersen graph, we will always have at least 2 edges of that 4th color. Then a little bit later, Stefan proved that the Petersen graph is the only bridgeless cubic graph that achieves this bound. And a little bit later, then Fouquet and Van Herpe proved And independently, of course, Kaminsky and Kovalik, these two guys considered the setting of multigraphs also, and they considered also higher degrees, and they proved that there is only a couple of graphs which achieve this bound or go over this bound also in the subcubic class. Otherwise, you have less than 2 over 15 edges. But okay, why is this important? Because as a corollary or side product of this investigation, they got that every subcubic graph admits 1, 1, 1, 2 packing edge coloring, which means that in proper edge coloring of any subcubic graph, we can or we can find an edge coloring of a subcubic graph in such a way that the color that appears the least number of times is a 2 packing. So the edges of this smallest color will be far away, at least a distance free. And Gastineau and Tony even conjectured that we can make it to be a 1-1 free packing edge coloring as long as we are not in the case of a Petersen and the Titze graph. So Petersen graph with another embedding is here, or another drawing is here on the left side, and Titze graph is a Petersen graph with one vertex replaced by a triangle. So that's why I have these two figures so similar. For these two guys, you need the fourth color to be at distance exactly free, but for all the others, it is conjectured that we can push them more far away. And this resolves the 1-1-2 problem or question. So if we have only 2 ones, how many 2s will we need then? A trivial observation is that at most 6, because we just make or take any 1-1-1-2 packing edge coloring, which we know from the previous section that it exists in our graph, and replace one of these free 1 packings with 5 2 packings. So you see, if I consider the blue edges, then I just want them to, or if I replace the blue edges with vertices and connect these vertices with edges if they are at distance at most 2, like this, and then color this graph, the violet graph, the vertices of the violet graph just properly, because then I will be, I would like to avoid these conflicts, right? So it's a proper vertex coloring. How many colors will we need for this violet graph? It will have maximum degree at most 4. So altogether we know that we need at most 5 colors by Brooks' theorem. So if that was replacing one of these ones with 5 number 2s, and we had 1, 2 from before, so K should be at most 6. That should be trivial. We can do a little bit better, but not a lot. So Gastineau and Tony proved that 5 colors are enough for every Bridges cubic graph. We extended this to all subcubic graphs, but it's not a very hard proof. So, I mean, you need to have some observation about what can happen in your graph, but this is rather straightforward result. Unfortunately, it's not tight. We do not have any example of a graph which would need that many colors, and that was expected, of course. In fact, the conjecture is that 4 colors of this distance 2 are needed at most. And this result, this number of colors, would be tied again by this graph, which is again k3 with one edge subdivided, which does not admit a 1, 1, 2 to 3 packing edge coloring. And this is the only known graph, which is the only known bridgeless subcubic graph, which does not admit such a packing edge coloring. So we can also ask whether this bound is achieved by somebody, by some other examples, or just by these guys, and it can be decreased even by 1 if we eliminate these trivial examples. So yeah, the problem here is what I will say also in the end, that we don't really know how to decrease this number 5. Number 5 was rather easy, but considering number 4 in the general case of subcubic graphs seems to be a little bit, not a little bit, but pretty hard. Nothing applies. None of the known methods are really successful in at least finding some reducible configurations or anything. So we have a lot of problems here with this bound. And a similar story is here with only one matching and all the others being number 2s. Again, trivial number of colors is comes from the strong edge coloring setting, because we know that 10 number 2s are sufficient. So 9 is trivial, and we were able to prove number 8. And again, the expected bound, the tied bound, is with number 7. Again, the k3 with one edge subdivided is not admitting the 1, 2 to 6 packing edge coloring. So a similar story as before. And that's the tour through this intermediate edge colorings, just initial tour, but I spent a lot of time on this. So if we remove all the ones I already said, we are in the strong edge coloring case. We know these two guys that need 10 colors. And it seems that if we are in the bridgeless setting, these are the only known examples. So it's known that they're the only known examples. We can append this guy to some other subcubic graph, but not really, but we don't know any other examples of bridgeless graphs. So why is this interesting? Or at least why is it interesting for us? We can make a little story around this removal of number 1s. And here you see this summary of the conjectures. So whenever I remove number 1 from the sequence, I will need to add 3 number 2s to the sequence, which is a nice story, and it would be even a nicer story if it would be the case also in the class 1 graphs. So when you have only a sequence 1, 1, 1 without this additional 2, so the graph which is colored properly with 3 colors, then everything works. Also, as you will see a little bit later, then the conjectures here in the middle are that 1 color number 2 less is enough. In the strong edge coloring setting, we need 10 colors just for this Wagner graph, which is in class 1. And also, you should not expect that you will be always able to just replace this guy, number 1 with 3 colors of number 2. You will need to somehow shift the colors around. It's not that you can fix the other 3 colors and then just try to color it optimally by replacing edges of just 1 color. yeah, and that's it. A few notes on proving techniques. So what is maybe interesting here is that there is nothing fancy behind. Nobody used any super involved method to prove any of the results I shown before. So you have this usual graph recoloring technique. You can try eliminating some substructures, so finding some reducible configurations. You apply combinatorial Nullstellensatz. There is for now no probability involved in any of the proofs presented, of the results presented until now. And maybe this is why we are so limited. We are really not, we do not know how to proceed with these general cases. It seems that we reached the level from which we cannot step up. But this was a little bit dry presentation, maybe. If you're not involved in this edge coloring stuff, then it's most likely that you will not be interested in these general cases, or maybe not even in the special cases I would like to present now in the remaining of my talk. But still, in the special cases or the special classes of graphs, a lot of things was done already for the proper edge coloring and also for the strong edge coloring. That's why I prepared a couple of sections. We will see how many of them we can cover in the remaining time. What are the constraints? What are the usual constraints when you consider edge coloring of graphs? When you see that you're not able to do it in general, then planarity is one of the possible options. Bipartiteness is one of the possible options. Large girth, maximum, limited maximum average degree, and so on. So we found a motivation for our further research in this conjecture due to Fodry, Jarfar, Schelp, and Tusa from very early 90s. They conjectured a bunch of things. The first was that at most 10 colors are needed to color every subcubic graph. So this conjecture was in a strong edge coloring setting. I just rewrote it to the S packing edge coloring language. So 10 colors are enough for strong edge coloring of any subcubic graph. This is resolved, as I saw. For bipartite case, 9 colors should be enough. This was also resolved, as I will show I will show in the next slides. In the planar case, 9 colors are enough. This was resolved just a couple of years ago by Kostochka and co-workers. This appeared to be probably a very hard case. Then if you have light edges in your graph, so you have a subcubic graph in which every edge has one end vertex of degree at most 3 and the second vertex of degree at most 2. So the sum of the degrees should be at most 5. Then 6 colors should be enough. This was also resolved a couple of times, also, even. One item in this conjecture is open. So if you have girth at least 6, then at most 7 colors should be sufficient. Now this is interesting, not just because of this S-packing edge coloring, but also from the strong edge coloring perspective. I don't know how much you are involved in the edge coloring altogether, but in the last few years, the strong edge coloring of, in the general case, is somehow interesting also for wider community, or for this also people who are on the top of graph theory community, but they are usually interested in reducing the upper bound in the general case. Now the current upper bound is still 1.772 delta square, while the conjectured bound is 1.25 delta square, so 5/4 delta square. And it's not really clear what one can do when the girth is limited. So if you have girth at least 6, the strong edge coloring appears to be as hard as if you don't have any restriction on the triangles, 4 cycles, 5 cycles. And even if you have larger girth, you are just able to reduce the bound just slightly. And the last item of the conjecture was that if a graph is bipartite and has large or girth higher than some constant, then it will always submit a 2 to 5 packing edge coloring. This was rejected technically just yesterday because, or today, because today our paper appeared on arXiv, but it was known a little bit a while ago already. So 5 colors will not be enough for all the graphs of arbitrarily large girth. You will always need at least 6 colors. Here we will come to a result of Bernard also. Do you remember the result, Bernard? You have some partial result in this area?
Yeah, we had some from GRWC, but multi-author paper.
Yes, 10-author paper in the planar case. So, okay, and what I wanted to do here is just to go briefly through several additional constraints in the last 5 minutes. So if we consider only class 1 graphs, what can we do? We know that then there we have 1-1-1 packing edge coloring, ordinary coloring with 3 colors. We proved with Hervé and Dimitri that 4 colors number 2 are enough in the class 1 graphs. So this means that we have reached the upper bound of the conjecture in general case, but in the special case of class 1 graphs. And we reached it also when we only have 1 color of number 1 available. So, and these two, surprisingly, or maybe not surprisingly, these 2 proofs are much harder than either the proof of the bound for proper edge coloring or the proof for the strong edge coloring case. So where you're in between, you cannot really use the techniques used for strong edge colorings nor for the proper edge coloring. So you have to somehow extend your consideration here. And again, the conjecture is that 1 color less is enough. So 1, 2 to 3 and 1, 2 to 6 should be enough. And we don't really know how to approach this. And another question, is the Wagner graph the only subcubic class 1 graph that does not admit a 2 to 9 packing edge coloring, which again seems to be not an easy question in the strong edge coloring case. I will only maybe go in the planar case also, just to cite Bernard.
If you want, you can have a little bit more time. It's not.
Okay, we will see how much I will spend. Maybe a couple of minutes. Yeah. So in the planar graphs case, we know that if we have a planar graph which is cubic, not subcubic but cubic, and bridgeless, then we have it will be in class 1 because of the 4-color theorem and the Tate's observation. These conditions are needed because K4 with a subdivided edge is not class 1 and it needs 4 colors. And here's another interesting conjecture which is not directly related with what I'm saying today, but maybe if you will be interested. So if you have bridgeless subcubic planar graph, which has at least 2 vertices of degree 2, so not only one, as in this case with a subdivided edge, but at least 2, then it will be in class 1. This is a conjecture by Albertson and Haas. It appears to be a special case of Seymour's conjecture, and it's only partially solved. A couple of results came out in the previous years. I didn't check yesterday if something new is known. Maybe Bernard will know, but the big guys are considering it, and it's still partially solved. So it seems it's in fact a really hard conjecture, although one would think it's not at first sight. As I said before, Kostochka proved, with coworkers proved that every subcubic planar graph admits a 2 to 9 packing edge coloring. And this is the only graph which is known to need 9 colors. For all the other subcubic planar graphs, we are able to color them with 8 colors. So, I mean, for all the graphs that people tried, they were able to color them with 8 colors. We don't have any particular bounds for subcubic planar graphs in these 2 settings. We just conjectured that 3 colors will be enough for planar graphs, 3 colors of number 2 and 6 colors of number 2, in this case with 1 matching, will be enough. So the same conjecture as in the class 1 case, but note that we have in planar graph case also graphs that need 4 colors. So this might be a little bit, it could be rejected more easily as the class 1 case, or not. There are infinitely many subcubic bridgeless planar graphs which do not admit a 1 to 5 packing edge coloring and 1 to 2 packing edge coloring, and we can construct them just by inserting this gadget to any 2 vertices of degree 2. So appending to these 2 vertices, these empty vertices, an edge and another whichever subcubic graph with at least 2 vertices of degree 2 we would like to insert here. So infinitely many cases. That's why the conjecture would be hard to solve, maybe. Okay, let's go maybe just skip the bipartite graph case and go to the big girth case. So the question was whether we can use only 5 colors for a strong edge coloring of subcubic graph if we have large enough girth. And 5 colors are needed already in the trees. So when you have no cycles in a graph, you will need 5 colors for strong edge coloring. And this is one of the reasons then. I mean, one of the reasons, the parity and all the other stuff that comes with it is the reason that 5 colors will not be enough in strong edge coloring case. And in the proper edge coloring case, you have graphs, cubic graphs, which have arbitrarily large girth, and they do not admit a proper 3-edge coloring, which was proven by Kochel. He proved that there are snarks which have arbitrarily large girth. And in this today's morning archive paper with Roman Sotak, which is also here today, Edita Machayeva and Martin Shkoviera, we proved that cubic graphs that admit a 2 to 5 packing edge coloring are precisely the covers of Peterson graph. So only those graphs will be the ones that will be colored with 5 colors. All the others will need at least 6 or more. And for this case, there was a partial result where Bernard was involved in this multi-author paper. D'Orsi and co-authors proved that if we have a subcubic planar graph of girth at least 30, then 5 colors will be enough. I don't know, Bernard, is this 30 decreased to some bound? Do you know some example of?
I'm not aware of a decrease of the 30.
Okay, so there is a bunch of results here, but nothing ultimate. So a lot of things is still open. Here's a summary of what I told today. So red numbers mean that we only have finitely many cases which achieve the upper bound. So probably the upper bound will be lower if we remove this a couple of cases. The blue results are our results, and the black bounds are the ones that need to be somehow proven. And that's it. Thank you for your attention.
Let's thank Borut for the nice talk. And questions? Are there questions for Borut? Yeah, we originally tried to do the same thing as Kostochka did, but we failed badly. Why we ended up with result? Well, let's see what we can do at least. Like, gross 30, okay.
Yeah, I was surprised to see the result. I didn't think it will be proven short in such a. It will be proven in this year. So because we were doing also something on strong edge coloring of planar graphs with Roman and Riste a couple of years ago, I think in 2014, and we just didn't think that the whole conjecture can be resolved, and then Kostochka came with this result. It's a nice and it's short paper. It's not a very long one, right?
Okay. More questions or comments? All right, let's thank Borut again.
Thank you.